Hello, welcome to this tutorial. I'm Anna-Lena Krause. I'm a master's student at Maastricht University where I study cognitive neuroscience. And I'm currently doing an internship at the Geometric Intelligence Lab at UCSB, where I study how the functional connectome changes throughout the menstrual cycle in women. And I'm studying that using graph neural networks. And that's why today I'm going to give you a quick tutorial on how to train graph neural networks on functional connectivity data. So, quick overview. I'm going to start off by giving you a bit of background information. So I'm going to tell you what a functional connectome is and why we care about them. Then I'm going to tell you how to compute them. I'm going to give you a very brief introduction to graph neural networks, just so that you're aware what they are. And I'm going to tell you why we should use graph neural networks for functional connectivity analysis. And then we're going to get to the practical part where I'm going to show you in Python how to train a graph neural network on functional connectivity data using a toy example. So what is functional connectivity? Functional connectivity represents how much brain activity in one brain region changes together with the activity in other brain regions. So it's commonly seen or used as a measure of communication or connection between brain areas. And why do we care about that? In many neurological and psychiatric diseases, functional connectivity is actually changed. So we can use functional connectivity to distinguish between diseased and healthy patients, and we can use it to learn something about these diseases. So how does one compute functional connectivity? Well, we start by measuring brain activity over a certain amount of time. So we put our subject in the scanner, for instance, for 10 minutes and tell them to do nothing. So what we have as a result then is we have a three-dimensional data of the brain. And for each data point of the brain, in fMRI that's called a voxel, we also have a time series associated with it. So what we then do is we take all our voxels and we group them into brain regions. And then we're gonna, for all the voxels within one time region, we're gonna summarize their time series into one single time series per brain region. And then when we have one time series per brain region, we can compute statistical associations between these different time series for each brain region. And the result is gonna look something like that, or at least it can be represented like that, like this picture on the right, where we can see an image of a connectome, where these nodes are the brain regions, and the lines between them are their connections, and the white little numbers are the strengths of their correlations. So, brief overview of graph neural networks. So graph neural networks are a certain class of neural networks that are designed to process graph structured data by specifically considering the connections between the data points. And these have been pretty effective for analyzing interconnected systems, like for instance, social systems, like for instance, networks of friends on Facebook, where the connection would be who's friends with who on Facebook, or biological networks like molecules, or also brain networks. And why should we use graph neural networks to analyze functional connectivity data? Well, because functional connectomes are actually graphs. So you can see it here in this picture. You can see a functional connectome, which is also a graph where the nodes are the brain regions, the connections again are the association strengths, which would be the edges of the graph, and the association strengths, the white little numbers, would be weights on the edges of the graph. So then let's get started with our tutorial. I'm just gonna open a little Jupyter notebook that I have prepared here. And so yeah, this is gonna be a little tutorial on how to train your own graph neural network on functional connectivity data. And we're gonna use a sort of toy data set from a Kaggle challenge from 2014. And this data set contains functional connectivity matrices of both schizophrenic people and healthy controls. And our aim is to use the functional connectivity data to classify the patients into healthy or diseased. So quick overview of the data set. We have 86 participants, 46 of which are healthy controls, 40 of which are schizophrenic. And for each of these patients, we have one functional connectivity matrix over 28 brain regions. So that would be a 28 by 28 matrix. And these contain the correlations between the activities of their brain regions. So what I did first here is I loaded our data set, and then I just quickly checked the shape of our data set. So you can see that this data object contains our connectivity matrices for all the 86 participants. So that's why it's 86 by 28 by 28. And then we have 86 labels for our 86 participants. And here I wrote a little code to visualize the data so you can have a better impression of it. So these are functional connectomes of both a schizophrenic patient on the left and a healthy control on the right. And on the x-axis of these graphs, you can see the 28 brain regions, on the x and y-axis actually. And each entry in this graph, or each little square in this graph, represents a connection between two brain regions. And the darkness of the square represents the strength of the connection between the brain regions. And on the diagonal, we have red because we don't have connectivity data for each brain region with itself. Okay, so here I import a few things from PyTorch, which we're going to use later. And okay, so let's start with training our graph neural network. What we need to do first is we need to take the data that we have and we need to convert it to a form in which PyTorch can work with it. So that we do in this little snippet of code here. So first we take both our connectivity matrices and our labels and we convert them to torch tensors. And then next, we're gonna make a list of graphs or connectivity matrices. So one for each patient, where we put each graph into this little sort of data object. And the data object has all the things that PyTorch needs to train a neural network on this data. So for instance, here X are the node features of the graph, which I'm going to explain a little bit more in a bit. We have an edge index and edge attributes, which together are a way in which we can represent the adjacency matrix that we saw above in a more efficient way. And then we have our labels, which are stored in the Y. So yeah, here I wrote all of that down. So the node features are features associated with the nodes of the graphs themselves. So in our case, we don't have any, unfortunately, so we need to find some ourselves so the neural network can train. But in other data, that could be, for instance, if we take a social network where each data node is a person and the connection between them is whether they are friends or not, then our node feature would be something associated with each node or person. For instance, that could be each person's weight or height. So that's our X. How we're going to come up with some node features, I'm going to show you in a bit. Then here the edge index and the edge attributes, that's how we represent our adjacency matrix for PyTorch. So to explain you this, I made this little graphic where I have this little example graph with 4 nodes. So this is how the adjacency matrix would look like. We have our brain regions, and each entry in the matrix is the connection that we have, or the connection strength that we have between the nodes. And then an edge index would be an object of the length of the number of connections, so 4 connections times 2, because for each connection between 2 brain regions, we put the 2 brain regions into our edge index. So we have a connection between 1 and 2, so we put 1 and 2. We have one connection between 1 and 3, so we put 1 and 3. And since that's not telling the whole story, we additionally need the edge attributes. And the edge attributes are just a vector which for each connection contains the strength. So yeah, we put all of this in this little data object. And of course, the labels are just the binary label of is someone schizophrenic? So that would be a 1, or not, which would be a 0. And what we also do here, which would be important to mention, is so we have in the end this little list with our graphs in it. And we split this list into training set and test set, with 80% into the training set and 20% into the test set. So we have 68 examples in the training set and 18 examples in the test set. And just for you to see, I displayed the first 5 examples from our training data, and you can see here our node features. I just remembered I haven't told you how to get it yet. I'm going to come back to that. But we can also see our edge index, which is 2 by the number of connections, and our edge attributes, which is the length of the number of connections. And here we have our label. And so how we got the node features is we basically just made an identity matrix, and we used this identity matrix as a sort of one-hot encoding. Okay. So the next step would be defining our network, and the network that we want to train is a simple graph convolutional network with 2 layers. We take this from PyTorch Geometric, and we define it down here. So in the init function, we define the 2 layers that it's going to have and how much channels each layer has, and then we define a forward function, which basically is a pass of the data through the network, and it takes in the data, it outputs a prediction, and our method that we are writing here defines in which order the data is passed through all the layers and activation functions that we have. So I just went for a very simple architecture here. So we have two graph convolution layers. The first layer has 28 input channels. That's because our node features have the length of 28, and 16 output channels. That is somewhat arbitrary. We then send our features through an activation function, which introduces a bit of non-linearity. And since it only lets the positive values pass, it also leads to more sparse activations, which can lead to more efficient representations within our model. Then the next layer, of course, takes again 16 input features. And since we wanna make one final prediction, because we have a binary classification task, so our output should have dimension 1 in the end, we reduce the features, all the features on all our nodes down to 1, and then finally put them through pooling layer where we average all the features from all the nodes, which are not now dimension 1, and we get one single number as an output. And in the end, we can use a sigmoid function to transform this output into a probability, which we then can use as a prediction for our classification. Okay. So the next thing we do is we train the model. One important thing to mention is here we define our optimizer, where we use Atom, which is just a very popular optimizer in deep learning. We define our learning rate, which controls how much we change the model parameters in each step. And we also define a loss function or a criterion, which will measure how well the model's predictions actually match the true labels of our graphs. And particularly we use the BCE with logits loss, which puts our final value from our model through a sigmoid function, which transforms it into a probability and then evaluates it with binary cross entropy loss. And yeah, so then next we define our training loop, where we use a train loader, which divides our data into different batches. And okay, sorry, I just lost my thought, stopped the recording and restarted recording. So I'm going to start again with the data loader. So the data loader helps us load the data in a way that our model can use it. We also define a batch size here. So the batch size means that it's the number of training examples that our model will see before the gradients are updated. And so then next we define our training loop. We use the data loader, in this case the train loader, to load our data in batches. Then we pass the data through the model to obtain a prediction. Then we're gonna use the prediction and compare it to the true labels and calculate the loss. Then we're gonna backpropagate the loss to compute the gradients of the model. We're gonna update the model's parameters using the gradients. And in the end, we're gonna accumulate the batch loss into a total loss. And we're gonna loop over this train loader until the model has seen all the examples in our data. Yeah, and then in the end, we return the average loss per batch. And next, we're gonna train the model for 100 epochs. So in each epoch, our model will see the complete data set. And yeah, so here I made a small visualization of how the loss evolves over our epochs. We can see that it goes down by quite a bit, which is nice. And yeah, of course, all this we did on the train set. So we trained the model on the train set, and now we're going to evaluate the model on the test set. So we also define a test loader on the test data. Again, we use the batch size of 8, and so we have this evaluation loop in which we put our data through the model to produce an output. Then we're gonna apply a sigmoid function to the output, which transforms it to a probability value between 0 and 1. And everything above 0.5, we're gonna say as true, so predicting that the patient has schizophrenia. Below is going to be false, so predicting that the patient does not have schizophrenia. And then we're going to calculate how many of the predictions we got correct with regard to our test set. And we can see here that we got quite a lot correct. We have an accuracy of 0.89. And lastly, we compute this little confusion matrix where we can see exactly what our model predicted and what was right and wrong. So here on the x-axis, we have the predicted labels. On the y, we have the true labels. We can see that they were 7 schizophrenia cases, which we correctly predicted as schizophrenia cases. There are 9 healthy controls that we predicted correctly as healthy, and there are 2 schizophrenia patients which we falsely predicted as healthy. So yeah, thank you for listening to my tutorial, and that's the end of it. Thank you.